Hi, I'm Jun Cowan and I'm here with
Bruce Hobbs.
Yeah, we did a joint presentation yesterday for Ore Deposits Hub, and we had a few hundred people attending that live talk, and we enjoyed it very much. Did you like the
I
session?
sure did. I enjoyed it a lot.
Yeah.
Yes.
I think it was fun. So I hope you people enjoy the presentation on YouTube. All right.
And if you want to ask any questions, don't hesitate to email us.
Yeah, just email both of us. Yeah, it would be good to hear from you.
So today we are very lucky to have Jun Cowan here, who's a structural geologist based in Fremantle in Western Australia down here. He specializes in interpreting mineral deposits at the deposit scale, and he's probably really well known for his thought-provoking geology posts on LinkedIn. So Jun was one of the conceptual founders of Leapfrog software, and he's used it to interpret and model over 600 deposits of many commodities worldwide since 2001. He offers consultancy services to the mineral industry clients around the world and continues to research new methods of presenting, processing, and interpreting 3D geological data for the benefit of mining and mineral exploration. So we're going to have a bit of an interactive talk today from Jun, and we're very lucky to have him. So when you're ready, Jun, you can go ahead and take us.
Great. Thank you very much. Actually, Chris, you can introduce this guy here that's right next to me. It was going to be a surprise.
Oh, am I allowed to do this now? Okay.
Yeah, well, might as well do it now because he's going to sit here and watch the show.
So we have a double treat for the viewers today. We have a surprise guest who's Bruce Hobbs. Anyone who knows anything about structural geology knows who Bruce Hobbs is, no doubt. He's a structural geologist who specializes in geomechanics and mineral exploration. He's currently an adjunct professor at the University of Western Australia and a research fellow at CSIRO here in Australia. He was formerly a chief scientist of Western Australia, and he's had numerous academic positions, many, I won't list them all. But Bruce Hobbs has worked on developing computer applications that simulate the mechanical behavior in fluid flow and heat flow, and then chemical reactions that govern ore deposit formation. The goal is to produce a predictive modeling capability that enhances our ability to discover new giant ore bodies. So he's published nearly 200 scientific papers, all in international peer-reviewed journals. He's co-authored 3 books on structural geology and fluid flow in the crust, including one of the bestsellers, An Outline of Structural Geology. We are all very, very blessed to have him here as well with Jun to give this talk today. So everyone hold on, it's going to be awesome.
Great.
Thank you.
Thank you very much, Chris. That was great. I'm going to switch over to the quiz. Can you see that quiz? This is going to be an interactive show. So yeah, it'll be hopefully about 15 minutes of the quiz, and we'll be discussing the outcomes of the quiz afterwards, and that'll take about 45 minutes. Hopefully the whole length of the presentation will be about an hour. Okay. So if you get your mobile phones out and type in that name, or that number up the top, at the end of the presentation, I will guarantee that you will see data from at least 7 mineral deposits. And also you'll be able to definitely learn a few things, hopefully, through our presentation. First of all, the question that I want to ask you is whether you're a geologist or not. So I just want to make sure that, that please refrain from participating in the quiz if you are not a trained geologist, okay? Because that'll skew the results. Just a quick question. Imagine a profile of a single upright fold. What do you see? Will it be synform or antiform? I'll give you 10 seconds for these answers so I can move right along. So most people are answering antiform. Next question, I have a dome and a fracture. So this is a bit like a structural IQ test, okay? This is the set of questions. That's a dome and a fracture cut horizontally. Is the fracture older or younger than the dome? Younger. That sounds reasonable enough. I have a set of, this is a dome with some faults cross-cutting it. Are the faults older or younger than the dome? I forgot to show the results last time. I'll show you the results this time. Oh, that looks reasonable, yeah? Okay, the green is marker unit, so it's a bit like bedding, and purple is a fracture, okay? We have to sort of consider this as a plane strain situation, so whatever you see inside the screen is the same as what you see here. Yellow represents mineralization. What is the relative timing of the yellow mineralization? Is it before the fracture, after the fracture, or both are possible? Both are possible. I agree with that. Again, yellow represents mineralization. Green is the marker unit. What is the relative timing of the yellow mineralization? Okay, I think I've got enough. Yeah, I mean, most people will say it's before the fault, but it can be both actually. I forgot to show you the correct result. Correct result. I said both fault and both are possible. So I mean, just covering the bases there. So note the fractures, right? Note the fractures and the black alteration. You can see the alteration here. What is the relative timing of the black alteration? Is it before the fracture, after the fracture, or both are possible? I forget to put the timer on, but anyway. Yeah, this one's a difficult one. In these questions, I'm asking you to answer in a way so that the black alteration comes in at one time, okay, and not over a broad period of time. So I think what people are thinking of, both are possible, is when they're coming in at different times. But because the fracture itself, you can see the black alteration abutting against the fracture, so it has to be after the fracture. That's the correct answer there. Okay, how about this case here? You have a mineralized unit that is fold form, and you have a purple fracture going right across it. The question is, what is the relative timing of the yellow mineralization you see here? Is it before the folding, before the fracture, after the fracture, or all are possible? All are possible, I agree with that one. That's the correct answer for that. How about this one here? You have the similar sort of geometry, but you have a fracture cutting across it and you have mineralization only on one side in this particular location here. What do you say about that? What is the relative timing of the yellow mineralization? Is it before the folding, before the fracture, after the fracture, or all are possible? Okay, this is the correct answer, which is after the fracture. Okay, the reason is that that fracture had to exist for this mineralization to abut against it, okay? Okay, we have sphalerite here, this red mineral in this core. And we have these faults here, which are very minimal displacements. What is the relative timing of the red sphalerite? Is it before the faulting, after the faulting, or both are possible?
June, I reckon you can give a little bit more time, maybe, just because some of the participants are having a bit of trouble voting.
Oh, really?
Yeah, but
Okay.
only just a slight delay here and there.
Okay.
But no worries about time. Add another 5-10 seconds to these things. Let us have a good look. Cheers.
Okay, I'll show you the correct one. In this case, it has to be after the faulting, not before the faulting, because the fault had to exist in order for this sphalerite to abut against it, right? There's minimal displacement here. You can see that this layer here, along here and here, that's been displaced that much, very little. But the mineralization itself, the sphalerite, there's so much sphalerite here and there's very little over here. So you can't explain this by displacement. It is actually a mineralization that happened after the faulting. So this indicates after the faulting mineralization. We're going to move over to looking at grade data. This is from Victoria. These are, I think most people are familiar with saddle reef deposits. This is from Ballarat, East Ballarat. And this is a plan view of the mineralization. You can see the high grades there and you can see the low grades. What is quite interesting about this image is that this is the atypical image of a saddle reef deposit, isn't it? Because we are looking at a plan view. We're not looking at it in cross section. Very unusual. But when you look at it, you can see these breaks. So this is the high grade. You can see that this is the very high grade here. There's hardly any grade here. And I've just drawn these very sort of roughly through those boundaries. And the question is, what is the relative timing of the mineralization here? Is it before the faulting, after the faulting, or both are possible? I guess the YouTube channel is quite delayed. So, okay, a lot of people said after the faulting, but not many people said before the faulting. So the correct answer is it has to be after the faulting. So the logic is that these boundaries must have existed before that mineralization to take place and abut against it, okay? How about this one? This is a plan view. This is a boundary you can draw across there. So the question is, what is the most likely relative timing of the mineralization? Is it before the fault, after the fault, or both are possible? I'll see if YouTube can catch up to me. It's quite delayed. It's about like 15 seconds. Oh, no, half a minute delayed. Yeah, I agree with you. It's before the fault. You can see a clear displacement. So the most likely answer would be before the fault. How about this one here? This is a strike line view of a deposit, and you can see very high grades here, and there appears to be a boundary that's running off like this. What is the relative timing of the mineralization? Is it before the fault, after the fault, or both are possible? Let's see what everyone says. Oh, show results. Both are possible. Okay, again, this boundary has to exist there before you have high grades bounded on one side. So it has to be after the fault. In this particular deposit, you have all grades showing here. You have some medium grades and higher. You have a fault running through here. And these are the high grades. You can see some continuity here, some termination. Again, what is the timing, relative timing of the mineralization? Yeah, well, I think you're getting the picture here. It has to be after the fault, right? Because the fault must exist in order for this particular mineralization to abut against that particular boundary. So it has to be after the fault. Now, this one's a rather complicated one. You can actually see the fold form, and we are looking in the down plunge direction. You can see the mineralization following a fold form, okay? And I'm going to show you a series of slides that show you, this is the stratigraphy, and from the stratigraphy you can actually measure the bedding and you can actually follow along. And there's the bedding model, there's the ore model here. These are digitized by mine geologists. And this is again looking along the down plunge direction. And these are transecting faults. So I'm going to rotate the image around so that you are looking down these faults. And you can see these faults running across here. They are cutting right across the fold axes. They're running along like this. And you can see the fold axes, the parallel grade that is being truncated at these boundaries. This is another view of it. This is all the grade data. And this is just the high grades, and you can see the arrows here. These are linear continuities of grades, which I think are representing fold axes. And you can see it swinging around right here. But the high grades are limited in this area only, and they appear to be fault bounded. They have very straight edges. Okay, I'll just go back a bit. This is a strike line view of those faults. So I'm looking at it from the south to the north, okay? The next image. And you can see a strike line view of the faults, and you can see that the grade's running along here. So this is parallel to the fold axes running through here, plunging to the left. And you can see in some areas it's thick grade and there's thin grade. There's not much displacement, obviously, here. There's a little bit of dip. Okay, what is the relative timing of the mineralization here? Is it before the folding? Is it before the faults? Is it after the faults, or all are possible? Oh, looks like we're going to run out of time now. Okay, I'm just going to let the guys from YouTube catch up. After the faults, brilliant. I'm kidding. That's great. Yes, the boundaries, these have to exist before the mineralization taking place. This cannot be explained by displacements along these faults. So that is correct. I think it's after the faults, and I'm absolutely agree with you. Now, how about this example here? Yeah, you can see the high grades. I'll show you the high grades. You can see the high grades here. This is a mapped fault, okay? This is a known fault. What is the relative timing of the mineralization here? Is it before the faulting? Is it after the faulting, or both are possible in this case? That's interesting. Yeah, that is interesting. It's after the faulting. That's what I think. It's after the faulting from the patterns that you see here. If you look at the pattern here, this looks like it's continuous here. This looks like it's been displaced. So you could match it up, but when you match it up, this thickness here is different from this thickness. So I think the mineralization is after the faulting. This is a plunging set of antiforms here, and these are the red arrows. These are the faults. Are these pre-fold or post-folding faults? Post-fold, I totally agree with you. So show correct. Yep, that's post-fold. I agree with that one. How about this image here? These are faults crossing folded bedding. So you can see the lithology is running across east-west, and you can see the faults that are cross-cutting it. You can see it highlighted in red. The question is, are these pre-fold or post-folding faults? See if YouTube can actually catch up. All right, the result, post-fold, but quite a few people have answered 17, pre-fold. That's quite interesting. And that is the correct answer. I think these are cross-cutting these bedding surfaces. These are post-folding. And I think that's it. Thank you very much. I'm going to explain to you what this actually means. We're going to go through each of these examples in the quiz, and I'll explain what they actually mean. And I'm going to do this with the deposit scale structural analysis method, which I have published recently in January. I'm not going to go through all the details, but basically what I'm looking at is a methodology to look at the large scale. So you're looking at regional to deposit scale and trying to predict what you'd expect to see in the outcrop. This is shown in the blue arrow right here in this diagram that I have in my publication. Now, the traditional way of doing geology is to actually work up from hand sample and outcrop and so forth. So why do we do that? It's because we've been taught to do that, really. I mean, when you go to university and learn how to look at rocks, identify features, you start with the rock sample and you go to the outcrop and so forth, and you can try and infer what is at the deposit scale. Okay, so that's in the red arrow. So so that's what I'm trying to do. Now, why would we want to do the deposit scale structural analysis from the outside in? Well, some of the main things that we want to see is significant structures that we would never see in fieldwork. Now, these things you'd never come across it actually in the fieldwork. In some examples that I've shown you here, they're actually hidden. You just can't see them. And being able to recognize these features at the deposit scale, looking at drill hole data, is actually quite simple to do. And as you've seen in the quiz, you're able to identify or correctly answer most of the questions actually. So, but if you look at deposits at this scale, it gives you a completely different view of the deposit, and sometimes quite diverging from the understanding of mineral deposits. And sometimes it's difficult to unsee or ignore these patterns, and hopefully you'll be able to see some of these patterns here. One of these things that I've been really interested in is syngenetic versus epigenetic mineral deposits. For those who don't really know, in the syngenetic mineralization model, you have the mineralization happening really early, like a VMS, SEDEX, sedimentary exhalative, volcanic massive sulfide deposits, and you have these komatiite nickel channel deposits as well. These are very early. And then what you have is deformation afterwards. You deform the rocks, and we're going to talk about mostly green schist metamorphism rocks and associated deformation with this deformation, green schist facies. And then you have the epigenetic mineralization, which happens during that time, during the deformation, or towards the end, okay? And a typical one we can think of is orogenic gold. Now, I found out from looking at hundreds of data sets that fold axes, shown in yellow here, they're really important when you want to identify exploration targets. But also these red crossing fractures and faults that cross these folds, these are really important. In fact, they may be more important than the folds themselves. So I want to describe this. Yeah, my title of the talk could have been distinguishing between epigenetic and syngenetic deposits. And I'm going to do that from the results of the quiz, hopefully. So we have synthetic folds and fractures that we had in the quiz. This is a situation here where you have, in this situation here, you can have all types of mineralization, syngenetic and epigenetic, and late epigenetic after the faulting. You can't tell the difference. Whereas this one here, when you have a fracture going right across the middle here, and you have mineralization is bounded on one side, or asymmetrical type of mineralization, you can say that the mineralization happened after the fracture of the purple fracture, but not before. So in that case, the mineralization is clearly epigenetic, and it has to be post-folding. Okay? And these features, these purple features here, these discontinuities, I'm going to call them Perkins discontinuity, and I'll explain to you why I call them Perkins discontinuity. The first definition, Perkins discontinuities are large planar discontinuities like fractures, faults, veins, or igneous dikes of various composition that cross-cut folded bedding and schistosity. They form during the late stages of orogenesis and exhibit contrasting ore grades on either side of the discontinuity. The asymmetrical ore distribution cannot be explained by fault displacement of a once continuous ore body that existed before deformation. So instead of saying all of that, I'm just going to call it Perkins discontinuities. And this was identified initially at Mount Isa by Bill Perkins through his thesis, PhD thesis, 1996, published in 1997. Here it is. This is a carbonate vein here, calcite vein. And you have, on this side here, you have sphalerite-rich zone, but there's no sphalerite on this side. And you can see that the displacement on here along this discontinuity is minimal. You can see this red line indicating the bedding. It's minimal displacement. So this is the barrier. And somehow the sphalerite mineralized on one side and not the other side. And this is an outcrop. This is an underground exposure that's tracing of a photograph. This thin section comes from this area here. So this is what it looks like. The orange is strong sphalerite here, and yellow is moderate sphalerite. There's no sphalerite in between. Now, when I first saw this, and I only really came across this in the last year, I thought to myself, wow, I've seen this type of pattern, but I've seen this at a much larger scale, at the deposit scale. So I figured, okay, if he saw this at this scale, we should be able to see this at Mount Isa at the deposit scale. So here's another example of Perkins discontinuities. These are these fractures here. We have the sphalerite asymmetrical mineralization on either side. So there's more here, there's less here. So let's go to the deposit scale, see what we can see here. We can see this S48 fault, okay? We're going to sort of zoom up to that. You can see this is just a rough position of S48 fault, and you can see that there's high grades over here of lead. On the southern side, very little. You can see it here as well. That's lead, that's zinc, that's copper, not so convincing with copper, but still there is this asymmetry. Now I'm going to look along the strike of this fault. This has been digitized by mine geologists. I'm going to just move through, and just note this high grade as I move through these sections. You can see it appears on one side, but not the other. Okay, I'll just go back again. High grade, low grade. And then you keep on going, and I'm going to show you the zinc. Zinc, there's high grade on one side of the fault. On the other side, there's very little and disappears. So this is asymmetrical mineralization, which I call Perkins discontinuity. So the Mount Isa deposit, which was considered a SEDEX deposit, is clearly the mineralization is post-faulting, which is post-folding. So it has to be late orogenic. The next deposit I want to show you is East Ballarat, which is what I showed you in this quiz. You have this sort of saddle reef type deposits here, and you can see these discontinuities. And this is a longitudinal view. This is bringing up the mine digitized faults, and you can see the discontinuities as defined by these faults. Again, the mineralization has to be after the faulting. So this is consistent with the orogenic gold model. It comes after the folding and after that cross faulting. Red Lake. Red Lake is in Canada, like Western Ontario. And you can see along this strike line view, this is the S2, the dominant cleavage running through here. And you can see, if you look at it, this is one that I've digitized along here, but there are other discontinuities that are low dipping. And you can see that in these quadrants, the grades are quite different. You can see this very high grade here. This is a fold-hosted gold deposit, and the fold actually itself continues on, but it's only present, the high grades are only present below this discontinuity. So again, the mineralization is quite late, and this is consistent with post-folding, post-faulting orogenic cold. And it's semi-consistent with what Dubé has written. But with the exception of those low dip features there, that wasn't really sort of discussed, mainly because their methodology is to do their work through field work and not really look at the grade patterns at the deposit scale. Campbell Dome gold distribution here. The Alpha Island fault is what this is digitized here. And you can see in some places, the gold is discontinuous. It abuts against that fault, whereas it's continuous in some other areas. This is a stereo image of it. I'm going to leave it up here. But basically, you can sort of view it later. You can see that the mineralization has to be late. It must be post-faulting. So the fault has to exist. How about the nickel deposits at Campbell Dome? This is considered to be syngenetic komatiite nickel. You can see the patterns are very similar. What I've done with the quiz is that I flipped this around so there's a mirror image of it, so you don't recognize it. But they really basically occur in the same area as the gold. And you can see the discontinuous areas here. This is discontinuous here. This appears to be continuous. There is supposed to be a displacement, a dextral displacement of about 200 meters here, but you can't explain this pattern here with just dextral displacement. If you put this back 200 meters, this will move over here, so that won't meet up. So there's a bit of a problem there. So this is a stereo image of the Campbell dome nickel. It seems to suggest that the nickel is actually post-folding and post-faulting, which is quite different from the traditional view that these are komatiite deposits. Oh, by the way, that reference to Wilson is incorrect. Okay, let's look at the Meleave deposit from eastern Kazakhstan. This is quite a spectacular deposit. It is part of the Zhiryanovskoye deposits. I can't pronounce it very well. But anyway, this is on the eastern side of Kazakhstan there. And it's ranked number 14 in the USGS list of VMS deposits. Here is a view of zinc. It's a down plunge profile, fold profile view. And you can clearly see that it is a fold profile. And that's the lead, that's the copper, and these are the lithologies. Now you can see from the lithologies, there's some lithological differences here that you can actually start digitizing the bedding, and that's what I've done here. You can see the bedding dips, local bedding dips, which I can actually interpolate and show the bedding. These are this is the red wireframe digitized by many geologists over the years, and you can clearly see the folded nature of the ore zone. So these are the trace of the bedding surfaces that are modeled, and that's the lithology, and they're the bedding surface models. And you can take the wireframes that were digitized by the mining geologists and take the normals of the triangulation, and you can see this sort of spread of data. But if you take the eigenvector of that from the great circle fitting in through there, and the rotation axis here is virtually the same as what I've done by hand by interpreting the lithological banding that shows the bedding. And yeah, this is quite consistent. It's very useful to do this. I'm going to show you the down plunge view first of the zinc in this case, greater than 0.5%. And I'm going to rotate into these transecting faults that I've digitized. Oops. And this is looking down these faults. These cross faults basically control the position of the high grade. So this high grade basically terminates here and also coincides with an area where you have medium grade and high grade here, and you can sort of draw in a plane. And you can see these are boundaries that are defined by these planar faults. And this is a stereo view. You can pause the video and you can view this in stereo. It's quite spectacular. Cross-eyed stereo view, so you have to practice how to do that, but there's plenty of tutorials on YouTube show you how to do that. This is a long strike view, so looking from here, this way to that way. And you can see that's the profile view. And these high grades are following fold plunges. This is the high grade right here. And you can see that this fault running through here, you can't explain this sort of thickness differences from here to here to be caused by fault displacement. The zinc is discontinuous right here. This is a stereo view, and yeah, it looks quite spectacular. Okay, this is another view. These arrows are linear zones of grade that I've digitized, and I've interpolated their trends using this, showing these trajectories. And you can see that these are basically, these trends are basically parallel to the fold axes. And this patch only is mineralized, and they are bounded, this area is bounded by these crisscrossing faults. So I think these are Perkins discontinuities. They have mineralization on one side. So what was considered as a VMS deposit, the Meleave deposit, is actually an epigenetic post-folding, post-faulting deposit. And this is just where this deposit is sitting. It's actually situated in an antiform. And in this area, there are three main deposits here that are all hosted in antiformal hinges. This is just one of them over here. A very consistent story. This is just a view of this particular deposit over here. How about the Rio Tinto deposit? It's number 2 in the USGS ranking of VMS, and this is an antiform as well. This is an interpretation here by Martinizard et al. In 2015. They interpreted this to be an extensional type deposit or rollover anticline, and then you have the mineralization happen during this process, early process, where the bedding is largely horizontal and then the whole thing is folded. Now you can equally, I reckon it's more convincing to interpret this as a syn folding deposit. So after the folds had actually formed, these late fractures are bounding up against this mineralization. You can see this type of faults in orogenic gold deposits. This is a stereo view of the Woolwonga deposit, and you'll be able to sort of see this in stereo once you pause it, and you can see these straight line breaks. Oh, this is a question regarding dome and fracture. So did this fracture form before or after the dome? Now, generally, you start off with flat bedding, so it's a sheet, and it can fold into cylindrical folds or domes. In this process, what happens is that the symmetry of the sheet changes to a lower symmetry object. So you have very high symmetry with axial symmetry, about the normal of the sheet here, and then you might have, and you get lower symmetry as you increase the deformation. So this is orthorhombic symmetry here. You can get monoclinic symmetry and triclinic. With triclinic, you don't have any reflection planes. Orthorhombic symmetry, you have two reflection planes. Monoclinic, you'd have one. So as deformation progresses, the symmetry gets lower. And with these two, you can have straight lines, okay? So straight lines are actually quite important. So the question is, did this fracture happen after or before the doming? This is the kind of question that was asked by my PhD supervisor, Friedrich Fortner, in 1976. He asked the question, what does this look like? What does the erosion surface look like after you destrain or retrodeform this dome, this antiform? And the answer is that it looks like this. So it's the same thing with fractures. If there's a fracture running across like this, and if you retrodeform the bedding, the fracture looks like this, and this looks like an unrealistic shape. So if you retrodeform this dome into a sheet, your fracture looks like this parabolic shape, which is obviously unrealistic. It goes from a low symmetry object to a high symmetry object with deformation, which is reverse to what you'd expect. So that can't be true. The Australia dome VMS deposits in the Pilbara look like this. They're in the red dots, the largest ones being Kangaroo Creek and Sulphur Springs. They're in a large dome, but they're well known for being virtually undeformed. That is what is claimed by these authors anyway. But if you actually look at the regional shape, they lie along a perimeter of a large dome, so the Australia dome. And there are these faults transecting this dome. These faults are interpreted as synvolcanic faults, as you can see here in the reconstruction by Martindale et al. And they show their present configuration here. This is the Kangaroo Creek, for example, here. There's only like a slightly tilted stratigraphy here. But in actual fact, it's part of a large dome. Now, the problem I have with these faults being interpreted as synvolcanic faults is that they have linear traces on the horizontal surface. So that means that these faults have a high symmetry and most likely planar, whereas the bedding that was also high symmetry and planar at the beginning of the deformation before the doming, that had the same symmetry. So how do you undergo deformation like this whilst preserving the high symmetry of the faults but deforming the bedding? This does not make any sense to me. Now, if you retro-deform the bedding of the dome and then look at the geometry of the faults retro-deformed, they would have a low symmetry. So it means that they would have had like a parabolic shape to these faults, and then they became straightened as the deformation proceeded. Now, this is just very unrealistic. And it's the opposite of expectation. You should go from high symmetry to low. And if you plot the bedding readings here, just shown on this diagram here, on a stereonet, they lie along a small circle, like so. And if you assume the faults to be vertical and you plot those poles, of course, they would lie in a large circle that has a vertical axis. And this is the subvertical axis. It goes 88 to 196 in this case. So this means that the bedding and the faults share a common axial symmetry. So I think they are related. So the bedding dips and the faults are related to the doming process. That's my interpretation anyway. Now, if you look at other domes, and this is a diagram from De Sitter's textbook from 1964, you can see a very similar fault pattern here in this dome and with the Australia dome here with the faults distributed. So I think this is related to the doming itself. Many VMS deposits are associated with foldings. So you'll find this out when you just Google search VMS deposits, specific deposits, and you can see maps like this. You can pull up maps from various publications. This is Windy Craggy from BC. This is the Kuroko deposit. These are cartoon depictions of the Kuroko deposit. Kuroko deposit actually doesn't look like this. This is a reconstruction. And there are many reconstructions on the internet. If you type in VMS deposits, and this is what I did yesterday, and this is what you get. And this has not changed in decades. You don't actually see a real map of a real VMS deposit on the internet. This is the Kuroko deposit once again on the left. Now, this is a real cross-section of the Kuroko deposit. So you can see that this is actually hosted in a set of folds, which was surprising to me because the way Kuroko was described to me by many people was that it was located in a back arc extension zone. So I would have expected to be lying in an extension zone. Like I didn't really expect to see folds. So this was a real surprise. So even the Kuroko deposit is located in a set of folds, and Kidd Creek is the same. This is The deposit is located in the core of a large plunging antiform. Hellier deposit is the same. This is a close-up of Hellier as published, but in actual fact, when you actually model the lithologies from the drill hole data, it looks like this. The Hellier deposit is located in a fold hinge. There is faulting associated with that. And the Q River looks very similar along strike of this fold closure. Boliden VMS deposit looks like this, and it is also plunging in a very steeply plunging antiform to the east. Paris Mountain VMS is also in a large antiformal closure. SK Creek is the same, it's in an antiformal closure. SK anticline. Metagamy VMS deposits are basically the same. It is distributed along the edge of this large fold closure that is plunging to the northwest. And on Vancouver Island, in the middle of Vancouver Island, you have Myra Falls VMS deposit, and that is actually in the crest of a dome. Noranda VMS, this is interpreted as a volcanic cauldron right here with ring fractures. But the way I see this is that you can actually see the bedding wrapping around, and you can see that this is a large anticlinorium that is plunging to the east. That's not really discussed by the researchers who work on the VMS deposits here. Iberian VMS deposits are virtually all of them are associated with antiforms. Neves Corvo deposit, which is part of that the Spanish deposits, set of deposits. This is number 6 in the USGS ranking of VMS deposits, and this is the diagram that I showed you in the quiz, and I asked you what is the timing of these north-south faults. This is a mirror image, by the way, of the actual map. And you answered and said these post-date the folding. Neves Corvo is located here, this right here. And you said that these faults post-date the folding, which I think is correct, but it is interpreted that these faults are actually volcanic. This is the proper map here. And this is a close-up of the Neves Corvo VMS deposits. And these faults are thought to be extension faults or sedimentation faults. But this is a, you can see from the contours that these have sharp boundaries, okay? So these are Perkins discontinuities, and the grade is controlled by these faults. But if you look at the map, these faults are actually late. And you can see the same type of straight faults, the Sturgeon Lake VMS deposit. This is the deposit. I saw a talk about this deposit in the 80s, in the late 80s. And these faults were called volcanic faults. And this was the first presentation that I saw about VMS deposits. Before that, I had no idea what VMS deposits were. And this was the first talk that I saw. And this is the moment that I just didn't believe in the story. Everyone believed in the story for some reason, but this didn't make any sense to me. So my search for the answer to this problem is going on for over 30 years. This is another map of the Sturgeon Lake. You can see these straight faults, which are called volcanic faults, and I can't see how that could be because you have fold closures in here, and these are cross-cutting it straight. Volcanic faults. So my question was, Why are so many mineral deposits located in antiform hinge zones? And this is where I inquired about this problem to Bruce, because he seemed to know a lot about fluid flow. So this is where I'll hand over to you, Bruce.
Thanks, Jun. So I just want to go through a few slides and illustrate kind of the physics behind what happens when you do have fluid flow and changes in permeability. So here's the first slide, and it's pretty intuitive that you inject some fluid at the bottom and it goes out the top, because these are all open systems, and they have to be open system, otherwise there'd be no fluid flow. And the yellow lines are the pore pressure contours. And of course, if this is of low permeability and this is of high permeability, it's pretty clear the fluid kind of can't go through here very much, so it goes around it. But the question then is, what happens if this is a high permeability lens sitting in a low permeability one? And I hope if I do something like that, it'll change, yeah. So now what happens is that the fluid gets attracted to the high permeability lens, and which is exactly the opposite. So it doesn't have to go around it, it has to go through it. And so the streamlines, the black lines, bend as they go into the inclusion. And it's nice to remember that if this surface dips this way, dips towards the center of the slide, then the streamlines bend like that. They go from almost normal to the interface to at an angle to the interface. And that's a normal bit of physics, and you can do all the maths and all that stuff and show that is true. So what happens now if we have a layer instead of a lens? So here's a layer, and this particular lens, this particular layer is of low permeability. So it does exactly what we already saw. The contours, the pore pressure contours bend as they go into the layer, and hence the fluid flow bends as it goes into the layer. So this is a low permeability layer. What happens if it's a high permeability layer? Well, of course, it's just the opposite. So the fluid comes in, the pore pressure contours bend the other way, and the fluid bends the other way. So in fact, this focuses the fluid far more than it does if it's a low permeability lens, which is kind of intuitively obvious too. So now let's go a little bit more complicated again and put some folds in. So here's a pretty simple chevron type fold, and everything that happens here is exactly what we've already seen with the two lenses that had high and low permeability. Now this has a high permeability, and the fluid pressure contours bend as before, and the fluid and the streamlines come in here, they get focused up here, and in this particular case, they come out again just there. But in here, they come right through, and they're much more strongly focused in the hinge than they are elsewhere. So, pushing on, what happens if there's an antiform and a synform? Well, we won't go there yet. Here's a rounded one rather than a chevron one. Same kind of thing. Fluid doesn't necessarily make it all the way to the hinge to get focused. In this particular case, there are two focal points for the fluid flow, here and here. So now, here's a series of antiforms and synforms, and you can see the same physics operates as it goes into this layer, which is a high permeability layer. It gets focused this way, it comes out, gets focused again, gets focused again. But in this synform, everything diverges. So there's no focusing of fluid flow in the synform. All the focusing is in the antiform. And this is a nice kind of stacked up geometry if you want to make a big ore body, because every successive layer focuses the fluid more and more until you finally get pretty strong focusing up in here. So here's a whole series of them, and you can see that you get slightly different patterns depending on what the amplitude of the antiform or the synform is, and slightly different focusing effects, but basically it's the same thing over and over again, that if it's a synform, things get divergent in there. If it's an antiform, everything ultimately gets focused pretty strongly. And if we zoom into this particular part here, you can see what's going on. This is a reactive flux, so it might be CO2 rich fluid that happens to contain gold. In fact, it will contain gold because the equilibrium solubility of gold is like 1 part P or 2 parts per billion, no matter what fluid you have. Nothing happens in the antiform because everything diverges, but everything gets focused into here, and the highest fluid flux is right there in this particular instance. That's where you're most likely to get an ore body, and the depleted exhaust leaves. It's really, really important to get the physics right, because there are two kinds of boundary conditions you can have. One is where the pore pressure is fixed at the base and the pore pressure is fixed at the top. And that's the normal way in which geologists think about it, because that's the way groundwater flow people think about things in the upper crust, uppermost crust. And it's kind of been inherited into the geological literature that the situation in the deeper crust is the same, that the pore pressure is fixed at the base. And what happens there, though, is that all the fluid gets diverted from the lens, from a layer, from a fault. It doesn't, some of it goes through, but most of it goes elsewhere. The other kind of boundary condition you can have is where you fix the flux at the bottom, and that means physically you have to fix the pore pressure at the top. But the flux at the bottom is more realistic because that's coming from some devolatilization source in the lower crust or in a devolatilizing slab or something like that. If you have a flux system, then everything gets focused into the layer or the fault that's there. So it's really important to get the physics right. Don't think about it as a fixed pore pressure gradient. You have to think about it as a flux gradient. And the reason for that is because if it's a pore pressure gradient, then it's not shown very well. It's not shown at all. But the pore pressure is fixed at the bottom, so the contour is parallel to the bottom. Here, you don't have that constraint. The pore pressure contours can change, and that's what causes the focusing effect. So the other thing that, so that's, first of all, shows that you expect things to happen in antiformal hinge rather than synformal hinges. This now is an attempt to look at right angles to the fold axis. So this is the fold hinge running across here, and it's in an antiform. So you can imagine that the bedding is dipping towards us out of the plane and away from us out of the plane. And in this particular case, there's a very small fault, and that means there's a gap in this low permeability layer. You can see that all the fluid gets focused into this permeable hinge and ultimately comes out here. So this is a really nice place to have an ore body, just here, where the flux is high. If you extend that a little bit and have a permeable bed along here with gaps in the permeability, so this might be highly fractured, highly veined, this is highly fractured, this is highly fractured, this is poorly fractured, and there's a gap, maybe a fault, there may even be a fault along here rather than just a gap. And you can see what the pattern flow is, that the flow comes in, it heads towards this. Jun likes to call this the inverted bathtub effect. So it's like you pull out the plug and all the fluid roars out, but that's exactly what's happened. And again, you get reactive CO2 rich flux coming in, which reacts with the right kind of rheology and the right kind of composition in here, and you get a depleted exhaust coming out. So that set of slides is supposed to show why you get things in synforms and not in why you get things in antiforms and not in synforms, and secondly, if you do have to have discontinuities along the fold axis, then you can get ore bodies and stopping abruptly and being a bit more dispersed on the other side of the fault. So thanks, Jun.
Great. Thank you, Bruce.
I can have wine now.
You've been having wine. What are you talking about? All right. How much time do we have, Tom?
We're coming up on an hour, 55 minutes or so of presentation time. So
Okay, so 5 minutes.
So
So my question is this: why are we living in an anime world? I'm half Japanese, so I can say anime correctly, and in the field of economic geology. What I mean by that is, you know, when you look up VMS deposits in Google, this is what you get: a lot of anime, you know, cartoons. This is what we see every day. We don't actually see a real VMS geometry. Like the Meleave deposit that I showed you earlier, that is a real geometry of what is regarded as a VMS deposit, and it is completely inconsistent with these models. And that is, and you can go to a lot of mineral deposits that I've modeled using drill hole data, and you get the same story. And I think it's because we have an implicit bias. And I talked about this, and I've done this talk many times, how geologists tend to see antiforms instead of synforms. And I wrote about it before. And if you imagine, ask a room full of geologists, do you see a synform, antiform? And most people say antiform. It's just, you can repeat this exercise over and over again, and it's quite fun, actually. So a computer would answer like this. And non-geologists, I asked non-geologists at UWA 20 years ago, and they gave me this answer. But geologists gave you this skewed answer, okay? In that particular case, 94% of the geologists thought of antiforms. So this is a normal roulette wheel. This is a geological roulette wheel. So it's quite, you're looking at two different populations here. And I think it's all to do with the fact that we actually look at these pictures in textbooks, including that Bruce Hobbs was involved in writing. You know, you see a lot of antiformal pictures. And this is the sort of information that we soak up as we get education, really get educated in geology. This is a diagram I couldn't publish in my last publication that it came out in January. I was told that if I included this figure in the article, I wouldn't be able to publish my article, so I had to take it out. Ironically, this is the only diagram that anyone can actually replicate using Google Ngram. You type in structural geology, geochemistry, and you get this plot, okay? And this is all from the scanned books that Google has made, and it's all indexed, so you can actually sort of see what the popularities of these words and phrases are over time. So until about 1940, structural geology was really quite dominant in the literature. Geochemistry didn't feature until the geochemistry, the technology really took off around the 1950s, and it really has dominated. Structural geology has been left behind, unfortunately. And I think this is what we soak up. I mean, what we hear every day is what we actually sort of, you know, form our opinions, unfortunately. But this implicit bias that we have within us goes into selective data analysis, unfortunately. And this is not something that's done purposefully. It's just sort of, it feels right, so you do it. So, and it includes ignoring previously observed information. And I don't have time to actually go into it here, but there's a lot of observed details by past geologists in the last 100 years that are just simply ignored. And I find that really quite distressing, because these geologists from the past were they're quite cluey. They saw the right things. One of the things that has been occurring in the economic geology fraternity is to actually simplify models or geological maps. And this is the map from the Ming VMS from the 1970s. And you can see the detailed structural details here. There's F2, F3, F4, and so forth. There's a very strong stretching lineation parallel to this fold. There's a structural map in the GSC in 2015, a lot of structural detail. The most recent map by Pilot et al. 2017 has no structural information. I'm just sort of highlighting this. I don't want to sort of be seen as picking on one author and workers. I'm just saying that a lot of VMS deposits papers are like this. There's very little structural detail on their maps. They just sort of take it out. Once you take out structural details, you can say almost anything about a deposit, including a straight syntectonic fault. Now, you just have to remember that this has a 10:1 stretching lineation. It is not possible to have a syntectonic fault that is planar, but that is accepted by the journal and is published. So the conclusion for me, geologists must critically observe and interpret structural data or geological data in relation to all other data sets at all different scales, not to be influenced by conventional wisdom, be skeptical about what you read in journals, always conduct a background check on the statements made. I think Perkins discontinuities, these sort of really easily identifiable discontinuities, can falsify a syngenetic model. That's all I can say right now. You might actually find these in your own deposit. So yeah, I think you should look for them. Oh, and a bit of a plug. If you're confused with your drilling data, please email me and link up with Bruce Hobbs and myself on LinkedIn. Thank you very much. Okay. I'd like to acknowledge the companies that provided permission to show the data. This type of work that I do, I can't really share it with anyone without the permission from various companies. So I really appreciate these companies providing me with the permission, and particularly with Kazink. They've been so supportive. They want to know more about their deposit, and yeah, it's been very good working with them. I also thank Tom and Chris for hosting this Ore Deposits Hub session. It's been really great, fun, and I have some references. These are not all the references, but these are the references that I have indicated in the presentation. So yeah. Thank you very much.
Well, thanks so much for that, Jun. That was awesome. And thanks, Bruce, as well, if you can hear me in the background there. I'll start with a question while we wait for them to come through. Jun, would you like to answer one of my questions, please?
Yep.
All right, so for that graph you had, so the era of structural geology and the era of geochemistry, do you think we're in the era of geochemistry now, as we have been, because there's new techniques, new analytical techniques that give us new data, whereas maybe the world of structural geology isn't necessarily getting that many new techniques that provide, new or smaller information. And so it's not really due to significance of either discipline, but because of the new techniques in geochemistry. And do you notice consequences in industry, in the working world because of that? Do you notice that there's a bias in geochemistry when you work with your clients? You find people ignore structures because maybe they're not pushing their face as much in university or in their training. Do you see this in your own working with clients?
Yeah. Yeah, definitely. I think there's a lot of biases in the industry. I mean, when I tell people that I'm a structural geologist, they kind of assume that I do the regular field trip sort of thing, you know, like you spend 2 weeks in the field and come to some sort of conclusion. I actually haven't spent any time in the field, really, not much, in the last 20. That's why my shirt is really nice and clean. It's I do most of my work actually on the computer and identify features that can be checked out in the field. And I work with structural geologists who do the field work, and they can check out the details independently. But there's a lot of biases, I think. Yeah, you're probably right about technologies. You know, geochemistry is associated with a lot of, Bruce likes to call toys, you know, like things that you can press buttons with. Same with Leapfrog. I mean, I helped to develop Leapfrog. That is a toy. You know, that doesn't replace geological knowledge or geological interpretation, but people are using it as if it's something that will give you answers, and it's just not correct. A lot of the times people say, well, let's see what Leapfrog says. It's as if it's like some sort of sage, you know, it's a thing. It's a black box. And unless you know how to marry that black box with geological knowledge, it is actually a completely useless tool. What do you think, Bruce?
Oh, well, I agree. I mean, nothing beats observation. And I always go back to Broken Hill. If you want to know who did the very best work on Broken Hill, if you want to know what the ore body actually looked like, go to Gustafson et al. In, I think, 1939. Because no one has described it since. They wave their arms and measure sulfur isotopes or something, and that's it. So
there you go.
I don't know.
You heard it from the Godfather himself.
One could also read that there's a worrying decline in geochemistry interest from that graph over the last few years.
I know. I don't know why. Like, you know what? They're so far ahead. I wouldn't be worried about that dip. To be honest.
I'm just joking.
What we need is an upsurge in structural geology. That's what we need.
Okay, a second wave.
Yeah, second wave. Yeah, exactly. Yeah, second wave. There wasn't even a wave.
Okay.
Well, it looked like structural geology didn't stop. It's just geochemistry overtook it, right? So they probably invented a mass spectrometer, and everyone was like, "Hey, cool numbers," and you know, everyone started pushing out numbers, right? We have a question here from. Oh, sorry. Go.
Yep. That's all right. Go ahead.
No, we just have one of our very own Jamie Kelly has a comment, a little question for you. So I want to unmute him, and he can have a little chat with you as well.
Hi there, June. Sorry I haven't been the co-host today. I had an absolute nightmare this morning on my laptop, and it's going to get punished by going to the repair shop. But I had a question just about the reasoning behind why we see a lack of, you know, structural data on things like geological maps in journals. And I just wanted to sort of ask whether you think that's because, well, do you think the authors don't understand the structure properly, and that's why they leave it out?
Well, with VMS papers in particular, I think it's because they are so convinced that VMS deposits are syngenetic, that they don't actually have to really sort of study the overprint. You know what I mean?
Yeah, and
so
I was actually
they don't actually sort of even bother documenting it.
And that was what I was kind of going to follow up on. I was going to say, is, you know, in your experience, do you find that you can have something like a syngenetic deposit, like a VMS, almost become an epigenetic deposit by the overprinting structure, like it remobilizes pre-existing mineralization, for example? Do you often find that's the case in some of your work?
I don't see any, I don't see any evidence of remobilization. Remobilization to me is that you have mineralization, syngenetic mineralization in one spot, and then you have it moved over to another spot. Okay, so you should see evidence of the syngenetic signature, but normally you don't see that. At the Meleave deposit, I don't really get into details, but when you actually sort of go into the field and look at it, everything is syngenetic. Everything is consistent with what you find, what you predict at the deposit scale prediction, right? It's, we see that. Bruce might have a comment on remobilization. Would you like to comment on that?
My only comment is that I don't understand it, that if you have something that's soluble at one place, and presumably it must be transported in fluids, it means that somehow magically it gets dissolved and then gets redeposited, often in the almost identical spot. I mean, for instance, in the Witwatersrand, people tell me that all the gold was in the particular beds, reefs, so-called, and it got remobilised and redeposited in exactly the same spot. Well, I don't understand the physics and I don't understand the chemistry behind that. So if somebody can explain it to me, I'll accept it, but I don't understand it.
Sorry, I said the Meleave deposit is syngenetic. I meant epigenetic, sorry. Yeah, sorry about that.
Awesome. Well, thanks for that. I appreciate that. Good talk.
I have a question that was sent through to me privately, so I'll leave the name out. But they have a comment about Mount Isa for you. So Mount Isa is not completely epigenetic, but subsea fault replacement is possible, and the fault could be a syn sedimentary fault. Can you explain your interpretation with any textual evidence?
You'd have to ask Bill Perkins about that one. Honestly, the scale that I work at is at the deposit scale, because that's the scale that really matters for mining companies and explorationists. So the predictions that I make at the deposit scale should be consistent with what you see in the field. So I tend to work with people who are field geologists, and they come up with observations in the field, and they have to match what I see at the deposit scales. But I cannot comment specifically to that question. Like, I can't answer that question. But I'm sure a lot of it is actually answered by Bill Perkins' papers, which are really detailed.
All right. Well, I got another question coming through. I'm going to go ahead and unmute you. His name is Justin, and he's GeoVox Terra here in the chat. So I'm going to ask to unmute him. Maybe he'll ask you this one directly.
Okay.
Let's see if he accepts. If you're there, Justin, you can ask John. If not, I can ask for you. All right. Okay. He wants me to ask for him. Here we go. This is all right. So he says, good evening. He's an exploration and core logging geologist in Alaska. He's working in the Donlin Gold Province. He studied structural and advanced structural geology in South Africa. His query is, the massive Donlin deposit is characterized by multiple episodes of fold and thrusting, post-folding, and at least 2 synvolcanic episodes. How much more critical is it that we focus on the plunging antiformal structures in the deposit, given the extreme amount of secondary thrusting and ubiquitous hydrothermal alterations?
Wow.
That's in depth. Yeah.
Look, what I do is just look at the grade. The grade actually is the most reliable data set that you can get from drill hole data. It's available everywhere. And you start dissecting, start documenting the really simple structures. And one of the things that I would look for are the lineation structures in the grade, okay? That actually tells you about the symmetry of the deposit. I won't go into the details here, but do that first. Once you figure that out, you can look down the plunge of that linear structure and you can start to see things. That would be my advice. So seemingly it can be very complex. A lot of people tell you about complex geologies, but in actual fact, when you actually look at the grade distribution in any deposit, they are very simple most of the time.
Okay, great. There was a question further up that we missed there from James, and he asked, is it possible to model fluid flow in Leapfrog in a way similar to the way that Bruce was showing us?
No. That would be the short answer. No. Leapfrog is a specific type of software, does one thing, okay? And it actually, I wouldn't even call it modeling. Modeling is, to me, modeling is something that is physical. You use physical principles, and this is the sort of fluid flow stuff that Bruce does and Alison Ord does. They're based on physical principles and physical equations that physicists have worked out long time ago. And Leapfrog doesn't do that. Leapfrog makes shapes using an interpolation equation in 3D, and it has no constraints in terms of physical, in sort of physics. So you can't do that in Leapfrog, unfortunately. You have to use other methodologies, which we are working on.
Yeah, as Jun says, it would be marvellous to take Leapfrog geology and export it into another one of these modelling codes. That's undoubtedly possible, but we just hadn't done it at the moment. But in any of those modelling things, it's really important to start really simple and work up to the complex, because if you get too complex, you don't really understand what you've modelled. And so taking straight Leapfrog geometry, which is often quite complicated, and trying to model it directly may not give you a lot of insight to start with. Ultimately it would, but you'd really have to simplify the geology to start with.
Do you think we can also begin to, at least in the simple cases, model these things in our heads, just teaching those kinds of thought processes to students and young geologists? Connectivity, permeability, structure.
Absolutely essential, I believe, and it's not all that hard. I mean, once you get your head around Darcy's equation, which is not all that hard, really, it's just the permeability and the viscosity and the pressure gradient, or the head gradient. Once students understand that concept, which you can be taught in one prac without too much trouble, then you can extend it easily into complicated geometries.
Yeah, good topic for a future workshop or a short course, maybe. I don't know. Think about that.
Oh, absolutely. Yeah, it's just fascinating. Yeah.
Okay, Jamie, have you got any? Chris, any more questions lined up there?
Yeah, I got one here. It's from Richard Siddle. I'm going to go ahead and unmute Richard if he wants to ask you directly. See if he accepts.
Can you hear me there?
Yeah.
Yeah, great. Yeah, so I was just wondering, back to the geochem versus the structural sort of discussion. You know, geochem data is very, very quantitative. We've got numbers and we can do noughts and ones and put R squared on it and things like that. Structural geology, probably with the exception of dips and strikes and stereo nets, tends to be more qualitative and observational. So does that sort of mean that we get more publications out of geochem because, you know, we like data and numbers, whereas if, you know, there's maybe less of an appetite for just observational geology?
Actually, all of my work involves really geochemistry, because I look at the assay data. That's geochemistry, like the abundance of gold or zinc or lead. That's information that is already in a tabular form. All I do is plot it in 3D and interpret those geometries in terms of structural architecture, really. So it's a combination of both. But the thing is, I guess a lot of people view structural geology as this sort of mystic thing. I actually don't view that way. It is very similar to geochemistry. It is actually, you can actually convert a lot of structural concepts into mathematics. In fact, that's what Alison Ord and Bruce Hobbs does all the time. They convert their structural concepts and knowledge into numbers, and they can simulate that using a computer. So it's actually, it goes, that those two things go hand in hand. Structural geology and geochemistry go together. But currently, what it's been done, the interpretation is all geochemistry without structural information. They will become incredibly powerful if you combine the two. And I'm doing it in a very sort of rudimentary way myself, but I think the future is the combination of the two. Yeah. Oh, here's Mel Hickman. She's a...
Richard, I have a question back for you. I just noted in your question that you used terms like in geochemistry, we've got zeros and ones and hard data, whereas in structural geology, you've just got observation. It just struck me as interesting, those choice of words, and I wondered if there's perhaps a bias there as a geochemist, which you came across as.
I wouldn't say I mean, I'm a resource geologist, so like Jun, I look at structures as well as geochemistry, and you know, I really like putting a stereo net up from alpha beta data. You know, I like looking at numbers, but to an extent, is it harder to turn, say, faults and relative timing of faults into zeros and ones, and
But
you know,
Richard,
publish a documentation?
Are just as important as zeros and ones of hard data.
Absolutely, yeah. But what I'm saying is that a reason why on Jun's graph you've got the peak in the geochemistry, because you know, people like to publish hard numbers and hard data in journals. Is there more appetite for that than publishing a purely geological observation?
I totally agree with you. I think Bruce would probably know more about this because I never really lived through that revolution in the 50s. But I think when geochemistry became really sort of cheap to analyze rocks, I mean, that must have really taken off. Whereas structural geology really didn't change during that period, or any period. Do you have any wisdom to sort of share with us, Bruce?
Well, you know, the real issue is that it's very hard to get quantitative in structural geology. But now you can, because there are drones and there are all sorts of photogrammetry techniques and things that enable you to produce 3D images of rocks in incredible detail. And that's the change in structural geology that I see coming. But the issue is that when you actually look at the geometry in a digital manner, structural geology in a digital manner, it doesn't fit all the models that people have been proposing for the last 50 years or so. For instance, there's a kind of imprint in geologists' minds that folds are periodic. Well, they aren't. They're nowhere near periodic. And Alison Ord has just published a couple of papers one of them in Journal of Structural Geology a little while back. And she shows there that if you take some of the non-linear theories in dynamics and apply them, then you get far more interesting understanding of what the fold geometries are about than if you assume that they just formed by ordinary old buckling. And I think that's the future. As we refine the way of getting far more digitised structural geometry, then there are a whole lot of techniques that we can apply to understand these things a lot better. We might have a geochemist coming.
Yeah.
Now I have to defend myself. I'm not a geochemist. I'm a geologist.
Yeah, I'm a geologist. I use it all.
I would like to make on that is, you know, I think in the scientific literature and anywhere else, we like sort of new shiny things. And I think if you look at where that big spike in geochemistry papers is in economic geology, that corresponds to the invention of the mass spectrometer.
Yeah.
And the reason we had a huge burst in and the electron probe also a little bit before that. But the reason we have this huge spike is because we've suddenly got this new toy which reveals a whole lot of things which we'd never seen before. I mean, I'm not a structural geologist, I don't know, but I don't think that there's been a similar sort of, you know, there's not been a sort of step change in methodology or technology, which
in fact, there's been a flood of structural geologists leaving economic geology. is really coincided with that change in geochemistry, that step up in geochemistry, and people just, structural geologists just got out of economic geology. I don't understand it, but it's, yeah, it just coincided at that time.
Just for the audience's benefit, June.
Steve Barnes, by the way.
That was Steve Barnes, yeah. Great, cool discussion. It looks like a nice afternoon there.
I just gathered all the geologists from the neighborhood, and Steve just lives a block from here, and Bruce, I can see Bruce's house from my kitchen window. So I can see Steve's.
Okay, so we got a couple of questions still here. One from Edine Bakker for me to read out. And it's, what would be the source of metals in an epigenetic VMS deposit if it's not symvolcanic or remobilization?
I actually don't know. Oh, Bruce knows.
Bring in Bruce.
Get out of the way.
I mean, to me, the answer to that is very simple. It's not so much the source of the fluids, it's the composition of the fluids, which are undoubtedly controlled by the source. But if you want to have an orogenic gold deposit, you need a fluid that is rich in CO2. The gold is there anyway, it's parts per billion, but it's there. The real problem is, how do you get it out of solution? If you want a copper deposit, porphyry copper, then at least, if I believe Wayne Burnham way back, he said that there's enough copper in solution in fluids that come off the slab to make any porphyry copper that you want. What you need is a mechanism for depositing the copper. So what you need a tectonic environment that produces the right kind of fluids in all these cases. And there's a recent paper that says that really important for porphyry coppers is the amount of H2O that's in the fluid as well. So once you have the geotectonic environment that produces the right composition of fluid, you can do anything you like. I mean, if you the one thing that I have a little bit of problem with, because I don't think there's been enough work on speciation of nickel in fluids, is how do you get a epigenetic nickel deposit? They exist, and they're even described in the Yilgarn, but presumably it's a carbonate again. It might be a chloride, I don't know, but it is presumably scavenged from the immediate vicinity of in the mafic rocks that happen to be nearby. But to me, you know, the actual sources of the fluids are often very, very clear and obvious. They have to be the right composition, but they always contain the right amount of metal anyway. And the real problem, and it's a major problem, is how do you deposit them? And that's not always very clear.
Steve Barnes not jumping in there on that nickel topic.
Yeah, I'm surprised he's not poking out. That's all right. We have another question come through. We got a question from Manuel Napia. I'm sorry if I said that wrong. You can correct me. I'm going to unmute you, and you can ask your question directly.
Thank you so much. Thank you so much for this interactive lecture. I'm very glad to be here and also to see Dr. Bruce. Well, my question is about the relationship between the mineralization and the host rock, especially in metamorphic environments, orogenic gold that Dr. Bruce mentioned recently. I found some coarse veins that are parallel to foliations. And I wanted to know, how can we tell the time relationship between those veins that are parallel to foliations? Because in this kind of deposits, the mineralization can be syngenetic or epigenetic or post metamorphism. So this is my question, how to tell it? Can we tell just by seeing the veins? Because we don't see any cross-cutting relationship, or displacement, they are just in the foliations? Thank you.
I think you really need to look at a whole bunch of veins to see whether some of them are folded, some of them are just dead parallel to the foliation. If they're all parallel to the foliation, then it would have to be post-foliation development. I would be guessing, but you'd have to actually look at a whole suite of veins to sort of determine that. You measure the orientation of the veins, and then you note the characteristic, you know, whether they're folded or not, whether they're stretched or they're boudinaged. Yeah, it's quite a complex sort of, you'd have to get involved quite a bit in trying to figure out the timing of the veins.
Okay, I've got a related question here, but I'll let Ismailia ask it anyway. Ismailia, I've tried to unmute you. There you go. You can ask your question.
Okay, thank you. So I wanted to know, I found in Morocco VMS, we have some syntectonic vents with the same mineralization of like bedding or layers. And at this time, I explained that these two mineralization are contemporaneous, but some researchers say no. I wanted to know how we can have the same mineralization in syntectonic vents and in bedding or layers in the same place. Thank you.
Yeah, if I understand the question correctly, just because you have bedding parallel mineralization, that doesn't mean that it's syngenetic or sedimentary. The sedimentary layers or formational layers are actually anisotropies that you have in the crust already. So you can have easily mineralizations that are parallel to those pre-existing anisotropies. So I think this is an argument that people have made in the past, that if you have bedding parallel mineralization, it's convincingly syngenetic. That actually isn't the case. If you listen to Bruce's segment on permeability, high permeability zones that are parallel to formational layers, and you can have mineralization would be parallel to those bedding layering. So you have to be very careful about that when you interpret this.
All right, thank you.
Oh, all right. I think we have one question left for you. This one's anonymous from YouTube, and it's actually a pretty good question. So here we go. What kind of reactions have you had after sharing your observation that many VMS deposits are epigenetic and they don't form as the prevailing model has suggested for, like, I don't know, many years now? Yeah, what kind of reactions do you get for that one?
Oh, they would just dismiss me.
You're wrong. You should feel bad. Get out.
I didn't really explain the whole point of the quiz. The whole point of the quiz was I expected the audience to actually agree with me. And largely they did agree with me, right? Or the questions that came up agree with my answers. So in some conditions, people totally agree that, you know, faults cut across a dome. Okay, the faults must be post-doming. But in other situations, when it's in a VMS setting, it's actually reversed. So I was trying to demonstrate the fact that depending on your mindset, your interpretations differ. That was the whole point. And I've been thinking about this for a very long time. I came across the VMS model when I was a student at U of T in the late 80s. And when I heard the story from a master's student, I didn't believe it because the faults were straight. These faults were cross-cutting, folded layering. They could not have been synvolcanic. They had to be late. But then as the years went by, I realized that the whole economic geology fraternity actually believe in this. And you can see examples of this, and there's the Ming deposit is actually an example of this. That was published, you know, they're being published now. so these straight faults cannot be early, or these interpreted synvolcanic faults can't be early. I mean, I'm convinced of that. I know that a lot of people disagree with it because the prevailing model is that, you know, these things are VMS. I just don't agree with it. That's basically it. I can't really sort of be clearer than that. So
no, that's I think that's interesting because it shows I guess the bad side of order deposit models, right? Order deposit models are supposed to help us. We pigeonhole things so that we can understand them better. But then I guess the VMS pigeonhole is that, you know, these things aren't epigenetic. So when you show us raw data, we go, oh yeah, you know, that's epigenetic. But then if you told us it was a VMS, you'd go, wait, hold on, I can't think about it like that. I have to change how I think about this, which is dangerous because you have a false bias in your head based on what you're taught, which is interesting because they're supposed to help us, not hinder us.
Yeah.
So if there is, we're going to close it off here, everyone. We've had a very long talk and long discussion. I appreciate you hanging out for this. Would you or Bruce or anyone else at your evening party have any final comments before we come off? Any announcements, anythings? Philosophies, theory, advice?
Actually, I have an announcement. Yes. I did ask Bruce to convert his textbook, his recent textbook with Alison Ord, into a series of videos. And I said, you know, I really like your textbook, but I actually don't understand it. You need to actually record some videos for the dummies like me, you know, like to understand, to be able to sort of communicate the main messages. So, and he's agreed to that. So we're going to record some videos and I'm going to organize it so he doesn't get frustrated doing the videos. And Bruce and Alison will do the videos. So that's an announcement. And I think that would be really helpful to people. And I'll make it freely available on my website, JunCowan.com. It's not up yet, but it will soon be. That's an announcement.
All right. Well, great. Thank you. Well, we appreciate the talk. We appreciate you having a bunch of other minds in the house to answer other questions and give us their opinions. It's quite a treat. And obviously having Bruce on was quite a treat. And thanks everybody for coming out. Everybody who comes to watch, we appreciate it. Obviously we need viewers. We're happy to have you around. We're happy to spend the evening or morning with you. Tom, who is talking later today when I'm asleep? I'm in Australia, by the way, so I don't stay up for the second talk. Who do you have, Tom?
It's going to be Evan Smith talking on big, beautiful diamonds. So a little bit of a change of tack for us, but should be great. Thanks a lot, June, and everyone.
Thanks, everyone.
Especially Bruce. That was great.
Thank you.
We'll email around that textbook link once it's up. Oh, sorry, those video textbook links. Yeah.
Great. Thank you very much. Thank you.
Cheers, everyone.
Bye-bye.
Bye.